This video should help with number 23 and achieve section 3.9. It's where we have to take the derivative of a function that is neither an exponential nor a power function whenever you have a variable base and a variable power. The best thing to do for problems like this is to go ahead and use logarithmic differentiation. So you see I took the natural log of both sides of my equation. And on the right hand side of the equation I went ahead and simplified, and I said as soon as I take the natural log of that base, that means any exponent can come down in front. So instead it creates a product rule problem on the right hand side. I have 2x squared times the natural log of x. After that, guys, I went in and I took the derivative. Derivative of any logarithmic function is 1 over what's inside the logarithm times the derivative of what's inside the logarithm. The right hand side, I just said derivative of the first, 4x, times the second, plus the first, 2x squared, times the derivative of the second. We know derivative of any logarithm is 1 over x. Now I went down and I said, well, I need to solve for f prime of x, so I would multiply both sides by f of x. And then the right hand side just simplified to be 4x natural log of x plus, this is just going to give me 2 times x to the first. Now, the way I got this cool final answer is I said, well, I know f of x is just the x to the 2x squared. In this group, I noticed both terms had a common factor of 2, so I factored out a 2x, sorry, not just a 2, but a 2x. I factored out a 2x. That left me 2 natural log of x for the first term, and the second term just became a 1 when you factored out the 2x. Now, I can bring this 2 out in front, and I did, and then when I multiply like bases, x times x, I add exponents. That's where the exponent 2x squared plus 1 came from. X to the 2x squared times x to the first is x to the 2x squared plus 1 power. Constant coefficient of 2 out front times the remaining group of 2 natural log of x plus 1. Now if you're thinking that's a cool problem, I'm thinking just like you. Love it.